In this video, we will learn how to solve problems involving the curious die. A peculiar die has the following properties. On any roll, the probability of rolling either 4 or 3 or 6 is 1/2, just as it is with an ordinary die. Moreover, the probability of rolling either 6, 1, or 5 is again 1/2. However, the probability of rolling 6 is 5/16, not 1/6, as one would expect of an ordinary fair die. From what you know about the peculiar die, compute the following. The probability of rolling either 4 or 3 or 2, and again the probability of rolling anything but a 2. First of all, I would like to write down what I know about this peculiar die. So I know that probability of getting 4, 3, or 6 is 1/2. Similarly, probability of getting 6, 1, or 5 is 1/2, and probability of just 6 is 5/16. Let's work on the first problem. We need to find the probability of rolling either 4, 3, or 2. First of all, I would like to point out that in this sample space that I listed above, there are 6 outcomes in this experiment. When we are casting a die, there are 6 possible outcomes. The probability of 4, 3, or 2 is taking 3 possible outcomes out of 6. And this event, getting a 4, 3, or 2, has a complement of getting a 1, 5, or 6. But we have a probability of that. Casting a 6, 1, or 5 is 1/2. So we can use the complement event to get the probability we are looking for. And to do that, we are going to say that probability of 4, 3, or 2 is equal to 1 minus the probability of the complement, which is 6, 1, or 5, which in our case is 1 minus 1/2 or 1/2. In part B, we're asked to find the probability of rolling anything but 2. Rolling anything but 2 means rolling 1, 3, 4, 5, or 6, so we can easily find the probability of that instead. I said easily because we have plenty of information given to us in here about this particular peculiar die, and I'm going to split these 5 outcomes into 2 different groups because these are mutually exclusive events, and addition property lets us do that. So we're going to write this the following way. Do you remember we have a probability of 4, 3, or 6 given to me? I have 4, 3, or 6 here. I'm going to separate them right now. So I get probability of 4, 3, or 6, followed by probability of what is left, 1 and 5, 1 or 5, like that. Well, in this case, I already know the first sum or first addend here is 1/2. I don't have a definition of probability of 1 or 5, but I have something similar. I have something right here that I can use, probability of 6, 1, or 5. So I'm going to replace this probability with 2 expressions. Probability of 6, 1, or 5, which I know is 1/2. But it's different from the above probability by an extra element of 6. So let's take it away. Probability of 6 has to be taken away to make this pair of probabilities in red equivalent to the one right here. So these two now, with this probability of 6 subtracted, makes them equivalent to this one we replaced by the 2. Okay, don't forget to go back and write this first probability in front, of course. Let me do that right now. Probability of 4, 3, or 6 is still there, and it's added to these 2. Now I think we are about to answer this question. Probability of 4, 3, or 6 is 1/2. Probability of 6, 1, or 5 is another 1/2. And probability of just 6 is a minus 5/16. 1/2 and 1/2 is a full 1 unit. Subtract 5/16 from that and you'll get 11/16. So my answers are 1/2 for part A and 11/16 for part B. In this next example, we have very similar setup. We're given probabilities of a peculiar die. Probability of 4, 5, or 6 is 1/2. Probability of 6, 3, or 2 is 1/2. And probability of getting a 6 is 5/16. Our part A is asking for probability of 1, 3, or 2. A 1, 3, or 2 has a complement 6, which I replace probability of 1, 3, or 2 by 1 minus its complement, which we have defined for us as 1/2. So I'm replacing probability of 4, 5, or 6 by 1/2, and it gives me 1 minus 1/2, resulting in 1/2 for part A. Part B is asking to find the probability of rolling neither 4 nor 5, which again, using the complement approach, it really means getting 1, 2, 3, or 6, but not 4 or 5. All right, probability of 1, 2, 3, or 6 can be separated because events are mutually exclusive. I can use the addition property and say probability of 1, 2, and 3 separately from probability of 6. Why would I do this? Because I know probability of 6, it was given to me, it's 5/16. And I know probability of 1, 3, or 2, which is I just found to be 1/2. So this expression, first probability is 1/2, followed by plus 5/16. Don't forget a common denominator. So 8/16 plus 5/16 is 13/16. My two solutions, therefore, are 1/2 and 13/16. Here is one more example. Probabilities given to us are the following. Probability of 2, 6, or 4 is 1/2. Probability of 4, 5, or 3 is 1/2. And probability of 4 is 3/16. Part A is somewhat trivial. Probability of anything but 4, we can approach this by using a complement event and use 1 minus probability of 4, which is same as getting anything except 4. And since we know probability of 4 is 3/16, we replace probability of 4 by that quantity, and the result is 13/16. Part B is much more interesting. We need to find probability of rolling a 1. Again, approach this using complements, and 1 minus probability of complement of getting 1 is getting 2, 3, 4, 5, or 6. So 1 minus probability of getting 2, 3, 4, 5, or 6. We don't have this full probability described to us, but we have some useful pieces we can use. So here's what I'm going to do. Pay close attention to this minus. Whatever I'm going to do to this probability to expand it, that minus in front of this probability will impact everybody inside of that expanded expression. As you can see, we're going to get to 3 different probabilities eventually. So these brackets or grouping symbols of any sort, you're welcome to use parentheses or braces or anything, they are essential. This minus will impact everybody in here later. Watch out. So I used a red ink here to show you the importance of these brackets here. So what am I doing? I'm splitting probability of 2, 3, 4, 5, or 6 into 2 more convenient groups. First group is choosing 4, 5, and 3 out of the 5 outcomes, because I know this probability defined to me as 1/2, so I can use it later. I still have 2 and 6, so here they are, they're separate. I can do this using addition property because these events are mutually exclusive. I continue because I know this number, it's 1/2, but I don't know this one. What can I do instead of this probability? I can use the probability of 2, 6, or 4, which I place here, but the line above doesn't have 4, so I need to subtract probability of 4 to make sure that my line, the new one, is equivalent in its value to the previous one. So what you see here in red, these two probabilities, this difference of these two probabilities is equivalent to probability of 2 or 6. Now I have everything I need to get rid of the probabilities and put their quantities instead there. All right, so 1 minus bracket First probability is a half, second probability is a half, the last one with a minus in front is 3/15. A half and a half gives me a 1 minus 3/16 within the group. I can find the difference here and then find the difference later, or I can instead, if you don't mind, distribute this negative inside of the group, and 1 becomes negative, while negative 3/16 becomes positive 3/16. Now what happens is that 1 and minus 1, they undo each other, they become 0, and I am left with just 3/16 as my final result. So let's conclude. First, part A, the outcome is 13/16. Part B, the outcome is 3/16.